Okay. When I first learned about the quasi-particle, its concept just kind of didn't ring to me very well until that I just found this book, and it has kind of interesting cartoon. Many of you probably know about this book, and at least if you don't know about this book, you will see there are a lot of beautiful cartoons coming out of these books. And then one of the cartoons is like this. It's actually describe the concept between the real particle versus quasi-particle using the analogies of the real horse. While the real horse is running across a dusty road that will be dressed by all this dust surrounded by the horse. And as a kind of one entity, still horse and the dust moving together. And this quantity is something like that we can call the quasi-horse. So this concept is kind of well captured in a sense most of the time when we just talk about the quasi-particle in condensed matter physics. Basically, when electron or any particles dressed by some of the other field or particles, such as phonons, other electrons, and kind of many different interactions, you can still kind of treat this entity as a kind of individual particle. Then naturally, this concept of the quasi-particle arises, right? Perhaps probably most important and interesting the example about using this quasi-particle is just electrons in the Fermi sea. Well, Landau already postulated in the late 50s when we just think about the electron on the top of this the Fermi sea as just one of the excitations of the elementary excitation of the Fermi sea. Turns out this single electron descriptions in the presence of the Fermi sea requires a concept of the quasi-particle. Once you just turn on the interaction of the electron between the single electrons on the top of the Fermi sea with the entire Fermi electrons in the entire Fermi sea. Part of the reason is there is a lot of scattering events can goes on for this quasi-particle. And if you just kind of think about the scattering process, basically you cannot just stabilize just one particle excitation for a long time because it will quickly just go through some of the scatterings and produce multiple particles after scattering events, right? But this Landau's the argument is, however, if the initial energy of this quasi-particle above the Fermi sea is small, and that energy difference becomes smaller and smaller. In other words, when I just put this quasi-particle very close to Fermi sea, you can quickly see that due to the arguments based on this phase space, they preserve the momentum conservation and the energy conservation throughout this scattering process. You can just easily prove that the scattering time of those kind of events quickly just kind of prolonged when the energy of this quasi-particle above the Fermi sea actually start to decrease. In other words, when I just create these particles right above this Fermi sea, those kind of the particle can live really quite long without kind of undergoing a lot of the electron scatterings to create decay into the other quasi-particle states. So hence that this Landau's quasi-particle concept, in other words, the electron, real electron with entire Fermi sea comes around. And the big difference here is by just doing this process, you will see that while that electron's charge and spins are preserved, electron mass and other dynamic quantity can be renormalized by just kind of interaction between the entire Fermi sea and this electron. In that regard, this quasi-particle in the Fermi liquid that we call is basically a good example that how we can use this the particle concept or quasi-particle concept to describe the entire condensed matter physics whenever we actually is suitable for the Fermi liquid type of the descriptions. Interesting enough, and that this is basically give us a way that I can just treat still the particle that I'm dealing with as just an electron, although it is quasi-electron, and just simply throwing the through type of the description, I should still be able to describe many things with the very simple single particle picture, right? However, the simple picture actually can break down, especially when just the interaction between the electron becomes so strong, such as you start to abandon this idea of this creating quasi-particle. And there are numerous of the examples. Basically, the school is about that. What type of the description, or what kind of situations we have to just abandon this type of quasi-particle type of the descriptions. Some of this well-known example is, for example, as you go down to lower dimensions and the Lorentz liquid type of the strong interactions will make this quasi-particle concept. You have to throw out this quasi-particle concept, and you have to describe this charge and the spin separations rather than this quasi-particle concept. Many of the strongly correlated systems, especially that the Q-plate type of the superconducting system, is believed to be that maybe the quasi-particle description need to be abandoned, and some other descriptions should come around. And there the examples are kind of going more and more, right? In some sense, just well-known BCS superconductivity is another good example that instead of this Fermi liquid type of the quasi-particle concept, the Fermi surface becomes unstable, that by just kind of making the Cooper pairs, and you need a different type of the ground states. It's another good kind of example that you can just kind of tag it on, that maybe the simple type of this quasi-particle concept is questionable in many of the cases. So my role today here is, of course, the list is very long, and there are many, many experimental evidence you can just kind of learn about this breakdown of quasi-particle concept. So rather than we will go through the many general things, I will just focus on the one particular material categories, then described about this the quasi-particle, breakdown of the quasi-particle description, or the unusual pairing of the quasi-particles I'm going to discuss. All right, so the material system I'm going to take on is my favorite, the van der Waals materials and their heterostructures. This set of the materials arises from the graphene about 15 or 16 years ago, now about kind of almost, 17 years ago, I would say. Starting out from this isolation of the single monoatomic layer of the materials out of the bulk host of the van der Waals crystals. Here, the van der Waals crystal means that it's a layered materials, and each of the layer that all the chemical bond is saturated within the layer, and between the layer, it is a weak van der Waals force to hold them together, such that in principle you can grow this material one single layer, or you can extract a single layer from the bulk host crystals, and that yet they are chemically stable. And the important part is, depends on the choice of your host material, you can get the various different type of the material properties. Especially if you look at the electronic properties, some of them becomes metal, semiconductors, superconductor, charge dense wave, even just nowadays topological insulators, and many more come around with various different type of the system. And perhaps more exciting things than just beyond this material description is they come around as the single material identity with not of the strong chemical interaction between the layer. Therefore, it is allowed that we can just kind of bring them together and stack them together to form the quasi three-dimensional structures back again with different kind of constituent. And that will just give us the excitement such that we can design the materials with more complicated forms with the different functionalities. And yet, this whole three-dimensional stacks can, in principle, be quite different from the original material we started with. So that has been the excitement. And it's not only cartoon that we just can create them. And one of the technique has been developed in the field for probably past 15 years is basically you can just extract these materials by mechanical exfoliation and restack them using this so-called van der Waals heterostructuring method. It's elaborated using of the sketch tape, but nevertheless, experimentalists now can produce this stack of the atomic layers where the interface is extremely clean, and yet you can choose different type of the stack type of the materials to form this type of the devices, right? So depends on your choices. It can be graphene, boron nitride, which is insulator, or maybe you can just have this transition metal dihydrogenide. Some of them become semiconductor and superconductors. An important part is you can make this stacks of the material as if the material scientists or material physicists that grow this type of material using the MB technique. You can just kind of mimic very similar atomic scale of the heterostructures. However, there is a more degree of freedom, as I'm going to kind of talk about the later part of these lectures on this type of stacking. Another important aspect of the experimentalist's capabilities, not only you can just create and stack these materials, in principle, you can just choose the shapes and the size of materials when you stack them, which allows the experimentalist to address each of these individual atomic layer in principle using this contact the coming from the side. Let me just kind of give you the particular example. So these are kind of some of the example. We just kind of stack multiple layers here that probably were 5 or 6 layers. Here's 5 layers of graphene boron nitride. Here's a transition metal dichalcogenide. But the important part is many of this material, especially if this material is electrically active material, such that we can make the contacts on them, we can make the contacts on individual layers and stack them together with either tunneling layer or coupling layer. And in the end of the day, we have the devices where that you have the electrode that address many of those individual layers separately. And this provides us immediate kind of the advantage using this type of system as a kind of interesting devices. MB-grown the semiconductor heterostructures, it is possible that you can make this contact in kind of couple of the layers. But it's extremely difficult if you just try to make the multiple contacts and multiple of the layers, simply because it is very difficult to dug out this MB-grown samples to make the contacts in particular layers separately. However, because we just create the stacks in the Van der Waals system by layer fashions, it's much easier and doable that you can make this multiple contacts. Perhaps most impressive example here is 9 layers of this stacking, and there is 6 layers of the electrically active layer. All of these layers individually contact on this type of the devices. So kind of device itself is a P and P type bipolar transistors. But nevertheless, experimentalists can make such a complicated geometries with many different contacts on this device, which allows us to kind of make the rather complicated devices that out of this type of heterostructures. That's kind of one of these experimental advantages it can present. Another exciting part is already mentioned, but this material comes with the various different type of the electronic properties. Semiconductors, superconductors, the transition, topological insulators, Dirac materials. There are the list of this, at least 100 or several thousands even nowadays, the materials that you can just apply very similar techniques to get this single monoatomic layers, right? And then you can just imagine what type of interface we will expect. Sometimes this interface is quite different from starting material. Good example is, say, if I have the niobium diselenide, this is superconductors. If I choose this is chromium germanium tellurides, which is magnet, so this is, you can make the interfaces between niobium diselenide and this the superconductor and magnets. And you can ask that at the interfacial state, what type of ground state to expect, right? Well, we know that superconductors and the S-wave superconductors and the ferromagnet tend to just kind of compete each other in terms of ground states. So what type of ground state do we expect? There is another straightforward answers there, experimentally as well as theoretically, right? So these are kind of good example that when you make the interface between this different type of electronic materials, what type of these interfacial electronic structures generally we expect. Sometimes, as you will see in the later, that even with the same material, graphene to graphene, one TMDC to another TMDCs, although this is the same materials, when you stack them together, if you just change the stacking angle, that often the interface will provide quite different type of the electronic properties that we started with. So in a sense, the sense of the diversity that we can create in this phase space out of these materials is another important aspect that this Van der Waals systems provide us as a good material platform. We can test out kind of many interesting physical properties. Right. So what I'm going to do today is basically, out of the 2 lectures, I will just try to cover some of the topics that this Van der Waals systems provide us to look at some of the interesting and unusual, the quasi-particle correlations or the pairing in the system. So I just kind of prepared a few topics here. Some of the topics is published already, some of the topics actually unpublished, but nevertheless it's kind of interesting mixtures that kind of discuss about the interaction effect in quasi-particle in general, right? So I'm not sure that whether how much times I will have to cover all of them. So there's no hurry. I think this is, yeah, I know. Now I have more than 1 hour, and then there's another lecture. So I will just try to kind of not to just rush it out and just try to give you ample time kind of for the discussions. And well, it is kind of difficult kind of talk to give because I'm surrounded by mostly by the theorists. So I think I will just try to be as naive as possible. You can just ask that, pose any hard questions. If a question is too hard, I will just kind of refer some of the speakers after me who is more expert on some of the concepts. So we'll see that rather than just rush it through, let's kind of dwell on some of this part and discuss more. I think that's kind of more of this the idea. So rather than I won't kind of go through that or zip through that everything, so I will just try to make them ample time for the discussion. So let's starting from the first topic. So first topic is about the concept of the quasi-particle right at the Dirac point of the graphene, and where that many interesting things can be discussed here. This work itself was done a few years ago, and there are many collaborators, and the main experimental collaborators is Jesse Krosner, who was my students, now graduated, Casey Fong in the BBN. Basically, both of them plays a most critical role in the experiments. And we have a lot of theoretical discussions, especially Andy Lucas is here, so I will just defer most of the hard questions to Andy later on, together with the Subir. And later part, we have some of the other discussion with other theorists. And then experiment actually is keep going on in my groups and expanded into the more exciting part of magnetothermal transport I'm going to kind of touch upon a little bit. Right. Okay. I mentioned about the graphene is the first material of the two-dimensional system. And in a sense, this material is also set the stage of the many other materials, especially topologically related materials later on, by showing that even though this rather simple system, just the carbon atoms arranged in this hexagonal forms, the electronic structure is rather easy to compute, use, and reasonably accurate single particle electronic structures based on type binding model. But it contains many essential parts that laid on the later part of the physics. Basically, the essential part of the graphene physics relies on this existence of Dirac cone at the corner of the Brillouin zone. And it's called the Dirac cone because if you just look at the dispersion relation between this quasi-particle in the electrons in the system with momentum and energy, there is a nice linear relations that the touching point of the conduction and valence band is located right at the corner of the Brillouin zone. Therefore, that there are two inequivalent Dirac cones there. So we often term as a valley in many of this two-dimensional system. But the important part is that the linear dispersion relation also related with that the chirality associated with these materials in each of the valley, where that this pseudospin or the layer in the sublattice indices is tied with this momentum to the momentum of the system. So it's indeed mathematically mimic this real Dirac equation or the wire equations we see in high energies. It has been studied quite a bit, and then there are a lot of important part of the physics actually arises near the Dirac point. I just kind of list only a few. The first part, I think this point is the protected from this simple perturbations, because this existence of this crossing point, what we call the Dirac point, is protected by the symmetry, especially time reversal symmetry and the inversion symmetry of the system of the lattice, right? So if you just, unless you break this atomic inversion lattice symmetry, time reversal symmetry, it's very difficult to break this degeneracy in the system. And of course, when I just kind of put this no doping into the graphene, Fermi level is right at this Dirac point, so such that usually this Dirac point, filling up to the Dirac point, the system remains as charge neutral. And yet this is a two-dimensional system, so using the gate that we can just tune the charge density away from the Dirac point rather easily. In the 2D with the linear dispersion relation, if you just compute the density of state, the density of state becomes 0 at the Dirac point, which means simply that there's not a lot of density of states that can screen the electric field. Therefore, near the Dirac point, that if you just consider electron-electron interaction tend to be very strong. Part of the reason is there is not much of a screening effect going on with lag of the density of state near the Dirac point. So electron-electron interaction becomes naturally quite strong, and it's very difficult to avoid this electron-electron interactions near the Dirac point. Therefore, that already at this stage, we start to get the feeling that when we just discuss about the physics near the Dirac point, that you have to consider strong electron-electron interactions. And when I just draw this band diagram and filling up the electron, already I start to use kind of the Landau Fermi liquid type of the quasi-particle concept, right? I just filling up that the single particle band. I still kind of want to kind of work on electrons onto this Dirac spectrum. Almost kind of I already implicitly using this quasi-particle that born out from the Landau Fermi liquid. And that question can be actually now questionable under this statement. There is a strong electron-electron interactions right at the Dirac point. In fact, this idea was captured already. Just considering how we can describe the Coulomb interactions right at the Dirac point, it turns out that effective fine constant, which actually describes this Coulomb interaction, is strongly renormalized because of this linear dispersion relation. So instead of this is a rather small constant, it becomes a very close order of the one quantity. Therefore, the electron-electron interaction can be quite important, which actually cannot be used easily the perturbation method, and that's what kind of I was told. Now, using this type of the idea, there has been some discussions in the theory, especially near the Dirac point, and the argument kind of goes kind of following way. Now, once you just dope away from the Dirac point, you quickly restore the ordinary, the Fermi liquid type of the descriptions in the degenerate electron system. And as I briefly mentioned in the beginning, in there, that important part that this scattering time of the electrons is probably related with the time constant, the energy, Fermi energy divided by the delta E square, and the delta E square in the finite temperature is replaced by the temperature. So if we just think about what is electron scattering time in this Fermi liquid, in the doped graphene, following through the Fermi liquid type of the idea, basically it just kind of decays as a T square of the descriptions. But you quickly see that if you're just staring at, if I just apply this into graphene and put the right at the Dirac point, we get into issues there, right? Basically, EF goes to 0, or in other words, the scattering rate, 1 over the tau, is diverging out when just EF becomes smaller. Well, that does not work well because in a sense, when we just think about this Fermi liquid, degenerate Fermi liquid, I assume the EF is larger than KT, much larger than KT. So this concept, I can just bring down to this near the Dirac point where the Fermi energy start kind of vanishes. And clearly, I should kind of come up with some other descriptions, how the electron-electron scattering can be described. And out of these discussions, especially Andy probably will mention about some of this interesting way that generalizes using the string theory type of the descriptions, it turns out the right way we can describe that electron-electron interactions right at the Dirac point or vicinity of the Dirac point is where I just kind of write down the electron scattering time is proportional to 1 of the T with this alpha, that this renormalized alpha that describes the Coulomb interactions nicely comes into kind of 1 over R squares, right? As you see here again, when the T goes down, eventually this tau becomes larger and larger, right? But never when T goes up, this tau becomes smaller. But the important part is their behavior is very different from this Fermi liquid behavior. So in there, therefore, that we just kind of put the kind of different type of the word to describe this type of the system. Often that we call this is a Dirac fluid that in contrast with the Fermi liquid type of the description. So what is the nature of the Dirac fluid? I think that's basically that described by this basically that crossing this, that you have the whole liquid, Fermi liquid far down here in the negatively filled the Fermi C. Positively filled the Fermi C becomes electron Fermi liquid. It's getting close to this Dirac fluid. So it's more like to kind of give a feeling of this quantum critical point, where at the finite temperature, physically what we expect to see here is Dirac point becomes thermally populated between the electron and holes at the finite temperatures described by this type of interactions. So, yes?
Just a quick clarification question. So, by equal sign here, you mean equal up to an order 1 constant, or is that strict equality?
You mean the
the equal sign, is it a strict
Oh, no. This, sorry, this should be the proportionalities, right? Yeah.
What is the dielectric constant that goes into your
All right. So okay. So that's endless the discussions even among the experimentalists and theorists. I think if I just use a vacuum where that there's no screening, other dielectric screening of the Coulomb interaction outside of this graphene sheets, the alpha is close to 1 indeed. Now, of course, if you just put the other dielectric medium, alpha tends to become smaller. What precisely the number is still kind of debatable. Even for in the vacuum, what is alpha? I think that's kind of all kind of slightly debatable problems. And there is some experimental evidence that the alpha, even without the any additional dielectric screening, certain frequency is close to something like larger than 1, few, 4, 5, or even 10. Some depends on some experiments. So I think there is a ranges of the uncertainty. What is precisely the number of the alpha? But it is clear that this becomes order 1 quantity in typical situations, unless you just kind of surround by the very strong screening medium, such as STO type of substrate, or that kind of the metal gates really nearby. Unless that type of situation, alpha is kind of order 1 quantity.
Can you make it also much greater than 1?
So vacuum is the best way. Right. I think that, again, that much greater means that, I don't know. I don't think it can be easily 10 or hundreds levels, but say something like the 3 or 4, 5. It's, again, depends on the frequencies and what type of the experimenter you just kind of rely on. That effective alpha can be something like the larger than 1 quantity. Can I just make the alpha larger than 1 by just putting on additional materials? I think
making BF smaller.
Yeah, I don't know. I don't know whether there is any experimental evidence so we can just present in terms of engineering. Yeah, there may be some of the active engineering is probably possible with certain frequency ranges, but in the wide band of the alpha enhancement, I don't know. Yeah. Okay, good. Right. So I think what I want kind of focus on is right at this Dirac point that I want kind of emphasize that the nature of the Dirac fluid can be described. There's electrons and holes that populate here, right? It's that in terms of this simple languages, this is a non-degenerated the carrier system. You can just kind of starting with the electronic the Fermi liquid, and then you just heat it up and eventually becomes non-degenerate. Difference here is right across the Dirac point is not only one carrier. So there's electron hole. They are non-degenerate distributed. In other words, that we can just deal with kind of the plasmas that where the electrons and holes are thermally populated and they are strongly interacting each other. So we already get the sense that some sort of kind of directions that relate with the plasma type of the physics, where that different species of the charges are strongly interacting each other and form this kind of fluidic states, right? Therefore, that many of the description, in fact, actually relies on so-called hydrodynamic descriptions, which has been developed in many of the different systems, including describing the strongly interacting plasma, right? So that's kind of one direction, so we can just kind of think about, right? And of course, this type of the description is kind of quite beautiful, but in the real materials, often that we are just kind of fighting to see the nature of the Dirac fluid in the competition with the disorder. And part of the reason that disorder becomes quite important is, well, disorder is basically changes the energy landscape in the sample. So if I have the homogeneous sample without any disorder, and all across this sample, basically I expect this nice the conical, the Dirac dispersion relations. And then if I just measure the transport, the conductivity across the sample, and if I just use a gate, usually behind of this sample, the back gate, that tune this the energy densities and measure the conductivity. Conductivity becomes the minimum right at the Dirac point where the charge density is tuned to 0. When you hit this neutrality point, I expect to see the minimum conductivity and goes back. And this is the typically conductivity measurement of the graphene sample. And just experimentally, we can locate where is my Dirac point in terms of the gate voltages, just looking at the minimum of the conductivity or maximum of the resistivity, right? However, this description is ideal descriptions without any disorder. When I just have the disorder, especially charge disorder, which is common in most of the sample, you start kind of change this potential landscape of the sample. In other words, especially when this your chemical potential is right at the Dirac point, where that there is a lack of this the electron interactions, your sample start kind of break down into the pieces and domains of the positively charged and negatively charged, depends on this the impurities you have in the sample. And often that this is what we call the electron hole puddle in the sample, and disorders that kind of create those kind of the domains of the electrons and hole puddles in the sample. And spatially, basically a Dirac distribution is moving up and down, depends on the locations when you take the dispersion relation. In this kind of sample, when you measure the conductivity will just round it off, of course, because you average out these sharp points in the spatially. And then measured the minimum point of the conductivity is not necessarily the minimum point of the conductivity you expect in the uniform homogeneous sample, right? So typically, experimentally, what you observe is if you're just dealing with a more disordered sample, your conductivity becomes wider, and it's not sometimes even centered at the right at the charge unitary point that they're pointing out the gate voltages. And also that there are scanning probe microscope, for example, is scanning electron microscope, scanning electron tunneling microscope done by the Jacobi's group 10 years ago, showing that samples shows this electron hole puddles that separate by the kind of few microns, hundreds of nanometer length scale that in this type of images, right? Note that this is already 10 or maybe 12 more than that times ago, and the sample back then was much more disordered, the sample we can have. This van der Waals stacking technique I just introduced in the beginning was only discovered just after this experiment was done. So this sample shows that when you have this typical graphene sample sitting on silicon wafer, silicon oxide wafer, this is a state-of-art of sample about 10 years ago, right? What happened was that the sample got greatly improved after this, and especially just using this, oh, by the way, it's in these typical cases that typical the electron hole puddle density, residual density is about 10 to the 11 electron per square centimeters, where that related with this Fermi energy, the modulation is about 40 millielectric volt. So in this type of samples, as you change the temperature from room temperature to low temperature, not much things happen because already disorder energy scale is taking over around kind of larger than room temperature. Of course, once you just create this type of the encapsulated sample, or at least using the boron nitride substrate, one thing nice about the boron nitride is it's very good crystals, and there's not much of dangling bond, there's not much of charge traps compared with the silicon oxide. So there is quite an inhomogeneous situation you can describe. For example, even for a sample that we create this graphene on boron nitride, look at this resistance at the right at the Dirac point and dispersions. It's kind of stick sharp, right? And the mobility on this sample is about 300,000 centimeter squares. It's about order of magnitude, almost 2 order of magnitude improvement with its silicon oxide. And this sample is already the very first generations. After this sample, there is even more incredible the improvement. Now this number is actually even order of magnitude larger in state of a sample we can achieve. One thing about this type of sample is once you measure indeed the Dirac point the variations, the residual density in the electron hole puddle is now almost order of magnitude, almost 2 order of magnitude smaller than what used to be. So it's less than 10 to the 10 electron per square centimeters. In the state of our sample, one can reach is even 10 to the 9 has been reported, which actually now reduce this the energy the ranges about kind of 10 Kelvin or about Kelvin range of the dispersions. I think that's kind of great things. So once you have this high quality sample, what you can do? What you can do is, again, let's just see that whether we can measure the conductivity of the sample and see what they look like. So this is the encapsulate graphene sample in boron nitride. So it's a kind of considers better quality. And I just measured this two-terminal resistance. And you will see that why I'm just using the two-terminal rather than four-terminal later on. But for now, this two-terminal resistance means it contains some contact resistance, but not a lot. But the important part is I want to kind of focus on this the conductance peaks near the Dirac point, right? What you see here is conductance peak becomes sharp in the low temperature. As you increase the temperature, conductance peak becomes smaller and broader, right? So clearly, we start to see the temperature dependence of this conductance peak at the near the Dirac point, unlike the disorder sample, which means resistance peaks. Thanks. Yeah. So we start to see that at least the disorder effect becomes smaller. The thermal effect we can see. The better way that we can describe this one is now, I just kind of plot that again in terms of inverse number, two-terminal conductance, right? But I just plot it out instead of gate voltages. I will just convert that in terms of charge density, and note that I just put into log scale of the density, and this is neutralities. But what you see here is that starting from the low temperature, well, the conductance more like the stay constant is extremely low density, but then it start kind of increases that as you go to the higher density, right? So that is expected. But now we just kind of change the temperature. And then this constant ranges becomes larger and larger. In other words, this peak becomes broader. Broader means that basically this is ranges that becomes kind of larger, right? Why peak is broadening here as you go to the lower, higher temperature? Of course, this is related with where that I start kind of thermally populate electron holes, and I start kind of populate more of the electron holes thermally. They all got carriers, can carry more of the current. That's why conductivity actually increases, right? So that's basically the idea we can start to see that this broadening of the peaks, right? And that broadening of the peaks basically tells us how we can just find out that the regions that related with the disorder limited versus thermally broadening, thermally populate the region, they simply say that low temperature, that everything is dominated by the disorder. Basically, this is ranges of where the disorder physics dominate in terms of densities, and beyond that is where that I expect to see that thermally populated carriers. So what you're seeing here is below something like in this particular sample, 25 Kelvin, still that you are limited by the disorders that create by the electron puddle, residual electron puddles. But above 25 Kelvin ranges, you start to see that effect of this thermally populated electron holes in the system. More likely you can just getting toward of this the Dirac fluid regions above the 25 Kelvin. So that's what you're seeing. Yeah.
And at low temperatures, it saturates at about 2 times 4e squared over h?
2 times of the 4e squared over. Yes, in this something like this, right? Oh, no, actually, it's 1.2 Kelvin, so 1.2 kilo ohm. This is just a bare resistance, not the resistivity. Right. So yes, I think so probably yeah. Right. Yeah. Right. Again, this minimum conductivity. There's many of the discussions. What is the true numbers and those kind of things. I don't want to touch upon that. Yes. Right.
Just a very naive question.
Yeah.
So wouldn't encapsulation with HBN also gap out the Dirac?
If you just put the graphene that the commensurate with the boron nitride lattice, then boron nitride, which actually break this inversion symmetry between nitrogen and the boron, can gap out the graphene. Typically, when you just can put this graphene sample with the boron nitride, unless you just try hard, they are not necessarily commensurated with the boron nitride lattice. Then basically there is no gap appears in the point.
Try hard to make them.
You have to align very closely, and you tend to uneat it, and then the graphene tend to actually match with the commensuration. I hope that later on, the later part of the other topics, I can discuss a little bit more. But you have to just specifically target the close the zero angle and match the top and bottom potentially, or that at least kind of one layer is strongly coupled to the graphene to gap it out. But often just randomly create a sample in the encapsulation gapping out is rare. Yeah. Okay. So if I just kind of plotted out this influx point, in other words, that where that constant becomes increases, and then I will just track, I will call that is my minimum density, or the precisely that is related with about half max of this full width of the this peak. That's more like this the indication where the temperature effect look like. So again, minimum point is more or less constant in the low temperature and start to increases, and increases is roughly following the t-squares, which actually expected, just kind of thermally population. So that tells us that where that I have the disorder dominated regime turn into the more like this thermally populated electron hole systems in the experimentally, right? So we start to see that at least we can see that there is a hope that we can look at this the Dirac fluid regime in this system, right? But what is the experimental evidence we can just present? That presence of this existence of Dirac fluid in this type of the system. I already showed the electrical transport at least here. Electrical transport, well, it becomes the thermal effects. I can see that here, but it's not kind of necessarily drastic. So there is probably some other experimental tool we need to present to show that this existence of Dirac fluid. So experimental tool that I can show you today here is just using thermal transport. Okay, so let me see how the thermal transport can distinguish between this Fermi liquid versus Dirac fluid in this system. So in the Fermi liquid system, there is a well-developed theory called this Wiedemann-Franz law. This is nothing but you have the comparisons between electrical conductance and thermal conductance, or electrical conductivity and thermal conductivity of the system. And it goes following. If you just measure thermal conductivity, and if you measure electrical conductivity, and take the ratio and then divide by the t, it becomes a universal number, so what you call this Lorentz number, or the Sommerfeld Lorentz. This is what you call the Lorentz number, and this Lorentz number is turned into the so-called this universal constant we call the Sommerfeld value, which only consists of the fundamental the constant of the physics, right? And the reason that this the detail of the material dropped out is kind of following. Simply, if the quasi-particle, in this particular case, electron or hole, carries heats and the charges, both of the cases, if you just kind of write down how the charge current and heat current should look like, they both involve of the drift velocity of these quasi-particles, right? So when I just take this ratio, of course, the details of this density will just drop it out, and therefore that I expect to see that there's some universal the constant appears, not depends on the material details there, right? So that's kind of simple way just I can put up there. Of course, I think this is one of the things we learn in condensed matter physics, and that there are various levels of the derivation of the Wiedemann-Franz law. Starting, you can just use the Drude model, you can use Boltzmann transport, or even more sophisticated method. But nevertheless, as long as we have this concept of the quasi-particle can carry both charge and energies, this actually worked it out. Not only theoretically, it has been actually discovered experimentally in the beginning. Wiedemann and Franz, this already in the late 19th century, that the law has been discovered. And it was quite robust. And this is a table that shows that ratio of this the Lorentz numbers, basically kappa over the sigma t, these Lorentz numbers, for the various different type of the metals and semiconductors, right? And with the different electrical conductivity, and especially in the metals, they are more like the 10 or 20% deviation from what is expected from the Sommerfeld value. Even for the semiconductor, as long as they're heavily doped and such that it becomes a degenerate electron system, their Lorentz number is deviating only 30 or 40% of what is expected. So it is rather robust. It's phenomenological, but nevertheless robust, telling us that in fact this concept of the quasi-particle that which actually based on this Wiedemann-Franz law is rather robust, right? But of course, this one is really based on the picture of the quasi-particle, the Fermi liquid system. Once Fermi liquid description break down, often the Wiedemann-Franz law also break down. There are a few experimental evidences is out there, right? For example, people did measure that when you have the one-dimensional wire, which can be described by the Lottinger liquid. As I mentioned, the Lottinger liquid is a good example. as in the one-dimensional Fermi liquid description is breakdown, they see the Wiedemann-Franz law is greatly the breakdown, especially when you have only a few channel remains into these wires, right? Another example is when the vanadium oxide, which is a typical system that you expect to see that metal insulator transitions happen. These folks actually measure also the thermal conductivity and electrical conductivity of the vanadium oxide nanowires. And they see that especially in the metallic regimes, very close to metal insulating transition ranges, the Wiedemann-Franz law is also breakdown quite kind of severely, about order of magnitude, and indicating that at least the electronic systems near these metal insulator transitions may not be described by this Fermi liquid. So there's kind of some of the experiments actually out there that shows that breakdown of Wiedemann-Franz law. However, you see that the experimental evidence often that present the breakdown of Wiedemann-Franz law is already a bit kind of rare. I mean, there are, but it's not quite common. And part of the reason that this proof of the Wiedemann-Franz law or violation of Wiedemann-Franz law is difficult, because the Wiedemann-Franz law actually make the comparisons between thermal conductivity and electrical conductivity. But this thermal conductivity that I just mentioned is not just the whole thermal conductivity of the system, but thermal conductivity carried by the carriers, right? Which means that somehow you should be able to measure thermal conductivity of the carrier system, electronic system only. But of course, in finite temperature, all degree of freedom can carry the heats, right? Especially phonons, right? So how we can extract only the carrier part of thermal conductivity reliably experimentally, that has been kind of difficult part that can realize in this type of the experiments. Now, imagine that if I have the graphene and just get into so-called the Dirac fluid region, right at the Dirac point where I have the thermally populated electron holes. What do we expect? So let me start with that first. So what do we expect? Without too much of this detail, at least in conceptual level, we expect to see that Wiedemann-Franz law is apparently violated. The reason is following. So if I have the right at the Dirac point, which means that a thermally populated electron hole carrier density should be the same because, well, it's a symmetric dispersion relation. They're symmetric in terms of the dispersion, so their energy density, if the electron carrier density is the same, their energy density should be the same. Let's simplify it for now, the scattering electron holes, and then all the mechanism is also symmetric. Then their drift velocity and the absolute magnitude is the same. So when I just kind of write down the charge current versus heat current, I can simply write down using just one numbers for the density, one number for the energy density, and one number for the drift velocities. In the nutshell, so what we expect to see is the following. If I just think about electric transport, in other words, I just kind of give you only the chemical potential difference, but no temperature differences, right? Basically, to carry this electrical transport from one side to the another side of the sample, when the electron moves in that one direction, hole moves opposite directions because they have the opposite charges, right? To create the current from electrical current from here, from this side to there, electron moves in there, corresponding hole moves in opposite directions, right? However, when I just kind of do the thermal transport measurements and the bias the sample the temperature-wise, hot to the cold, now there is a thermal drift of the electron and holes from both hot side and cold side. So they move kind of together. So that's basically what we need to describe the electrical conductivity and thermal conductivity cases, right? When there is no interaction between the carrier, basically we expect to see that all of this process kind of individually happens. But interesting thing happen. What if there is carrier-carrier interactions there between electron-electron, electron-hole, hole and hole, but more importantly, electron-hole. And that actually poses kind of interesting problems. If I just throw in the interactions, especially electron-hole interactions, in this electrical transport cases, electron holes move in the opposite directions. So any frictions between electron hole can slow down the electrical current. So electrical current can decay simply because of electron hole interactions into the both electron hole populated region. While the thermal transport, basically they're co-moving together. So these interactions between electron and hole will not decay the thermal current. So from this comparison, we expect to see that thermal current, thermal transport is more like the stay there. Electrical current probably decays. And therefore, we expect to see that if you ask what is a Wiedemann-Franz law should look like, if I just make this Lorentz ratio, kappa over sigma t, this must be larger, because the thermal is dominant now, larger than what is expected from the Lorentz number. So we expect that the Wiedemann-Franz law is violated in the upper side at the neutrality point with this simple description. Of course, much more elaborate description is needed, as I'm going to describe it later on, to what exact kind of numbers are evaluated, but actually that is kind of expectation. Experimentally, how we can measure this one? As I said, experimental approach onto the sample is rather elaborated because you only extract this electronic part. So here that we rely on two parts. The first of all, we want to kind of make the sample small enough such that the electron and the phonon coupling becomes weaker. In other words, if my sample size is smaller than electron-phonon scattering length scale, I would say that if I heat up the electron by Joule heating, then heat may just remain the electronic system only, not leak through the phonon system, and the heat will be transported through the electronic system through the channels and dump into the contact, right? So I want kind of decouple the electron and the phonon system by just making sample size small enough, small compared to the electron-phonon length scale. And this can be achievable in graphene rather easily, because electron-phonon coupling, especially electron to optical phonon coupling, is something like the reasonable size in the finite temperature. Therefore, that I can stay into these arguments up to the reasonably high temperature, something like 100 kelvins or 200 Kelvin even in some cases, right? And the other one is then I should be able to measure electronic temperatures only. So I can heat up the electron by Joule heating, but I want to measure electron temperature. And the way that we measure the electronic temperature is using the Johnson thermal noise. So basically, if you just measure Johnson noise due to the fluctuation dissipation theorem, then we know that noise is related with the temperature of the system, electronic system. So simply measuring the Johnson noise of the electronic system, I should be able to measure the temperature of the electronic system. So that's kind of the way that we set it up for the Johnson noise thermometry. And then we just use a Joule heating to heat up the sample, electronic system of the sample. And then, of course, a central part of the channel becomes hot, and this will decay into the, as you approach the channel, where we assume that when you approach it to the contact, where we assume the contact is basically bulky materials that stay as constant temperature. And then we simply just kind of, as a function of the Joule power heating up, how this the Johnson noise changes, and from that relations, we should be able to extract information about what is the thermal conductance or throughout this the electronic system to the channel, and from there on we extract this thermal conductivity the measured values. So this is kind of way that we just did it, and indeed when I just heated up the sample, that Johnson noise temperatures increases, and how fast this temperature increases is related with how good is how bad is the thermal conductivity of the sample. Okay. All right, so from there, that we can get this thermal conductance, and thermal conductance as a function of bath temperature, we start to see that it's increased linearly, and at some point actually start kind of much rapidly, and it's a superlinear behavior is generally seen in typical sample that we measure in the graphene. And this is linear, the slope. If we just take the slope, this is basically exactly that what Wiedemann-Franz law just expected. Note that if the Wiedemann-Franz law works, where is it? Copper is proportional sigma t, and sigma is not much of changing with the temperature, and the t is just temperature. So expect that if the Wiedemann-Franz law works, there's a linear change of the copper with the t. right? Where the slope is basically this Zommerfeld value, and exactly that's what we are seeing in this type of curve, experimental measure, right? And it becomes superlinear at 100 Kelvin or 150 Kelvin-ish. Part of the reason is now the electron-phonon coupling becomes stronger at higher temperature. So heat is not staying in the electronic system. It starts to leak through the phonons, where the phonon contribution of the thermal conductivity sets in. So therefore, we are measuring something combination of the electron-phonon contributions, right? So already start to see that this experimental technique, and at least at this size of sample, we need to stay something like below 150 Kelvin-ish. Of course, if you change the device design even smaller, we can push this temperature even higher, right? So that's something limits we can see that. But what I'm saying here is basically we see the Wiedemann-Franz law seems like to work in this sample. And part of the reason it should work, and also it checked that we are doing the right experiments at this point, is this is at finite density, right? So question is, what if now I change the density and getting to near the Dirac point? So yes, yeah.
An experimental question. How clean does your sample have to be at that scale?
It's a very delicate problem. So I don't want my sample becomes completely ballistic, right? Because in a sense, I want to define conductivity, not conductance, right? So I don't want kind of contact is dominating my sample, right? So I need to define my, I want kind of describe my sample is a kind of diffusive transport enough such that I can define the conductivity, right? But at the same time, I don't want kind of my sample is completely dominated by the impurities, especially charged impurities, right? Because then I cannot see that this thermally populate the electron holes in the fluid. So there's kind of detail of the balance, and you have to just work it out, right? All right. Yeah. I'm going to show you in this sample. So so I will just replot that with this one. So yeah, I will explain. So let's say that this is sample I showed you before, right? So this is a device, a two-terminal device, and then you see the why I just use a two-terminal because I want to use this Johnson noise thermometry. I need kind of go back to the two-terminal. And the density I just showed you before is something close to there. Now I just can move this density close to something near the peaks, but not right at the peak, something kind of halfway through, right? So I'm just showing here that thermal conductance that I measured as a function of temperature. And it's actually stay more like the constant and goes up, right? I just kind of for the comparison, the how well matched with the Wiedemann-Franz, I just measure in this sample. This is thermal conductance, but convert this into the electrical conductance and then multiply with the Zommerfeld value with the T and replot with the temperature, right? And this is a line that going through this conductance, electrical conductance times of the Zommerfeld value. So if the Wiedemann-Franz law works, basically this, the orange curve and blue curve should exactly overlap. What you see here up to say something like 100 Kelvin, oh, well, it's kind of, there's some deviation here and there, but at least it's kind of reasonably close, right?
Is there any understanding of the wiggles?
Yeah, well, experimental errors or this inhomogeneous or some things, right? I don't think the wiggle is so important. I'm going to tell you why, because the signature I'm looking for is much more than this wiggle, right? So what if I just kind of bring it to the even closer to Dirac point, or actually right at the Dirac point? This is what is happening, right? That's why I'm just kind of showing that let's not dwell on this wiggle. Right at the Dirac point, so at the low enough temperature, yes, I still have the kind of this, the following to the more like the Wiedemann-Franz law, but it start kind of really deviated around kind of 30 or 40 Kelvin, and it's picked up and start to decrease and increases again. I think probably this few point increase is related with now eventually phonon becomes relevant in the system. But there's a kind of huge changes in terms of thermal conductance here, right? The one better way that I can just show that is instead of just showing in terms of temperature dependence, let's now park at the one temperature and sweep the density, cross the Dirac point and see what is happening. So at the 20 Kelvin, again, I'm showing you that now the sweep through the gate voltages, right at the Dirac point, away from the Dirac point, more like my thermal conductance, electrical conductance overlap each other, right? Wiedemann-Franz law works at the 20 Kelvin. right? 40 Kelvin, right at the Dirac point, there's blips now, right? So there's some deviations, right? Now, there where that I start kind of see the deviation. Around the 75 Kelvin, now it's undoubtedly that Wiedemann-Franz law is kind of strongly breakdown right at the Dirac point. And this breakdown is about factor of the 20. It's a huge deviation, so we see in this sample. So must be that there's kind of descriptions should be in there, right? Okay, so what is kind of happening here? So the better way to describe all of these things, in fact, it shows now the samples in terms of the Lorentz numbers. So I just kind of show that. I plotted out, experimentally measure the thermal conductance, experimentally measure electrical conductance, multiply this one, divide by these numbers with the temperatures, will give you the estimation of the experimentally measured the Lorentz number. And I can compare that with my Zumwalt value L naught, which is only defined by the KB over E, right? So take this L over L naught as a ratio, and I can just plot that out in terms of the density that's tuned by the gate voltages and the temperature, and that's basically this plot. So here's the temperature, here's the density, and blue color, dark blue color is close to 1, where that close to Lorentz numbers, right? So everywhere else is more like the Wiedemann-Franz law works in the sample, except that right at the Dirac point, around the Dirac point, and certain temperature ranges. Right, that's kind of what our data shows. Can I explain why actually there is a deviation like this? The first of all, note that I just plotted out this the green dot, which is basically the trace of the minimum of the density. This is a point that I just extracted out, that conductance does not change with too much of the density changes, but then conductance starts changing with the densities and temperature. And this is a point where how the disorder and thermal broadening is happening. For example, that I just plotted out what is a nice expectation of how the chemical potential to change in the sample. Basically, using the dispersion relation, this one more like to show the square root type of behavior, right? In between this conical section is ideally what I expect to see the non-degenerate the carrier system. Outside of here, that I expect to see the Fermi liquid, right? And now experimentally measured value of this curve tells us that basically around this temperature is where that disorder is more dominated. In other words, basically the nice deviation of the Wiedemann-Franz law is lower bounded by where the disorder is dominated in terms of temperature. Basically, this is a disorder dominated region that we restore back to the disordered, the degenerate system, such that Wiedemann-Franz law hold. And above this temperature, eventually, and higher temperature, electron phonon scattering cannot be ignored anymore, and especially electron phonons inner scattering, which is kind of more important part, will dominate it, and they break down this the simplistic description we have in the beginning in the hydrodynamic descriptions. So more or less, we explain that why we expect to see that these violations of the Wiedemann-Franz law is nicely cornered within the region that we expect to see. Okay, so that's yes. So only way that I can change this disorder fluctuation is making the sample cleaner or dirty, right? So that's kind of things that I'm going to discuss in a moment. Yes?
So we see a dark blue region on the very top of the plot as well.
Yeah.
So it reverts back to Wiedemann-Franz?
Well, my experiment becomes quite unstable beyond this one. That's why I chopped it off. I think if I just look back, this, right? Sorry. Yeah, something like this, right? It kind of goes up again. And as I mentioned, that my experimental technique works before electron phonon scattering becomes kind of important, because then I'm not measuring any more of this electronic contribution of thermal conductivity alone, right? So interpretation beyond this one is basically it's complicated, right? Okay, so now we can just do a little bit more quantitative analysis. Quantitative analysis can be done, again, just kind of look for the previous papers done here, that considering the hydrodynamic description of this Dirac fluid, there's nice descriptions made that if I just measure the L, compare with the L naught, basically expectation of this, how the L changes, the Lorentz ratio changes, depends on the density with this N0, which is again related with this the scattering mechanisms with this LC. And there's a nicer scaling law is expected with the various range of the disorder in the system. So what you can do is basically just following this theoretical descriptions, we just kind of plotted out the L of L naught, L of LCs, and basically we can collapse down all the samples with the different type of the disorders. And amazingly, that many samples actually fall into this universal curve we just kind of plotted out. And this universal curve contains two fitting parameters in here. One is basically the enthalpy of this Dirac fluid, and the other one is the scattering length of this electron to the impurity that kind of changes the conductivities. Now, the scattering length, the elastic mean free path, is something that is not a fitting parameter. In fact, we can extract it from our electrical conductivity measurement. And from there on, in principle, we can extract this, what is the enthalpy densities into this system. And if you just plot it out, that's basically enthalpy densities increases temperatures in the system that we measure with various different type of the disorder. So at least we start to see that some of the description is happening. If you just push this idea even further, this enthalpy enthalpy of this fluid is also kind of related with the entropy of the systems and the viscosity and entropy of the system. And there's a nice relations that you can extract it in fluid dynamics that take the ratio of viscosity with the entropy of the system. There's a minimum bound exists, and it seems like that this more like to satisfy this these bounding values of this system. So there's kind of more things we can push on. Theoretically, that going further of this system, you have to really consider very carefully that how this puddles actually plays a role. And they actually did kind of take this one in the full description of the Andy Lucas here, that take this description of the full description, hydrodynamic descriptions, including the disorders, and to try to explain the data that we have more on the quantitative level, and there is a reasonable success. There is even further that the other type of this, the more of the fluid dynamics or the even ADS-CH type of the description is needed to describe the description. So there's kind of more theoretical description is needed, especially using these hydrodynamic techniques to understand the data, right? So at this point, I mentioned that seems like the Dirac fluid, existence of Dirac fluid and reasonable description is happening. What is going beyond, kind of further, right? So you notice up to here that I just described nothing about the magnetic field in working presenting the MagLab. So of course, next level is what if that we just turn on the magnetic field? What type of things can happen? So this is kind of simple data we had. So this is the gate voltage and this is the magnetic field, right? And then I just plotted out what is L over L naught ratio. So basically, I measure both the electrical conductivity and thermal conductivity contributed by the electric field, and measure so-called these fan diagrams of the Lorentz ratio. And you start to see that nice fans actually indeed shows up, right? If I just cut it different the density, you will see that if we just cut it high density, basically that the electrical thermal resistance actually goes up with the field. At the same time, electrical resistance goes up with the field. And in fact, they shows a nice ratio, the same behavior. In other words, basically at high density, the Wiedemann-Franz law seems to work. In fact, it turns out component by component it works. It's not surprising in a sense. High density, we still kind of describe the Fermi liquid with modified magnetic field. But interesting things happen when you get down to the low density. Basically, we start to see that there is a substantial deviations. And then, of course, we start to see that this quantum Hall effect appears. Note that this is a two-terminal measurement. So we have this nice plateaus appears in the two-terminal conductance or resistance. But at the same time, we start to see that this nice oscillations appears into our thermal resistance data. It turns out thermal resistance is even more sensitive than electrical resistance. For example, in this particular sample, we don't necessarily, the fractions appears in the nice plateau, right? But in the thermal signal, we clearly see the fractions even appears into our thermal resistance signals, right? So in some sense, thermal resistance is more sensitive, and Wiedemann-Franz law is apparently kind of strongly violated here. It turns out this violation is not really intrinsic in some sense. A little bit of detailed studies, the way that we measure the thermal conductance is just through the noise measurement. And this noise measurement, in Jones noise measurement, is extremely sensitive to where the power dissipation is really happening. Of course, in quantum regimes, all this power is dumped at the contact because everything else is velocity conductance. So in a sense, it is expected once you get into quantum regimes, basically you have the most of dissipation is happening at this contact near the hot spots, so not necessarily picking up some of the intrinsic things. But nevertheless, this is a good sense that we can just see that where the quantum effect kind of sets in this type of system. Now, if you are interested in more of the intrinsic thermal conductance properties under the magnetic field, you therefore need a different type of sample geometry where the heat dissipation is not localized in some of the hot spots. What type of samples we can do that? Well, that samples basically we can just turn into the so-called Covino type of the device geometry, where that basically the inner contact to the out contact, the current is flowing the radial directions. And there is no set edge states appears even under the magnetic field. And this type of geometry is a nice way that we can just look at the thermal transport. So this is an ongoing project, so I don't have much things to say. But what you are seeing here is if you measure electrical conductivity, electrical resistance, and the thermal resistance or conductance across these Covino devices under the magnetic field, we start to see that positive magnetoresistance, both electronic and thermal sectors, it seems like that they have some relations outside of this heavily doped regime. So again, Fermi-Lecuyer regime, it seems like that we restore back to the Wiedemann-Franz. But even with it is magnetoresistance. But near the Dirac point, there is a strong deviation, especially strong suppression of this magnetothermal resistance at near the Dirac point, and even change the sign at higher temperature. All of these things start to tell us that there is something interesting things we can do with the magnetothermal transport. In fact, I would claim that this magnetic field is a tool that we can separate the electron hole motions in the thermal transport, should contain some of the interesting information we can extract. So that's basically something I want to kind of say about this thermal transport and the violation of Wiedemann-Franz law. Yeah, time is up, right? So I have great worries because I prepared 5 topics, and this first topic take up the 1 lecture is even more than 1 hour. So I should probably restructure my talk. But anyways, I don't want to, as I said, I don't want to rush it out. I want to kind of discuss something. So I will stop here, but let me get more questions if possible. But let me just try to go back to my initial slide. And I feel like my reality and ambitions here. So what I want to kind of ask is, oops, what am I doing here? Yeah. All right. So I figured out that there's no realistically that cover all of these things, right? So I just kind of stop here at the first lecture. So I have still 4 topics, right? So over the before end of the lunch, because I'm giving the talk right after lunch, so choose one of your favorite topics. Let me start with that topic. Yeah, most likely I will go for this one. I think this is kind of rather relevant for the.
Yeah, for the next lecture,